Hello, good morning. Thanks for coming to my talk, No Solid Evidence. And I prepared an alternative title, if you like. Hello, my name's Derek Graham. I left my social media thing at the bottom. You can find me on most things using @DJ Graham. I'm a principal developer at Sage in Newcastle, and I'm working mainly on Azure Cloud and .NET. But more recently, I've been working with JavaScript and React. Been writing code for a while now, and sort of as well as my day job, I run a programming camerata for junior developers at work as well. I've been doing that for about 8 years or so now. On top of that, I also run our local .NET Microsoft Stack sort of user group, NE Bytes. So what I want to talk about today is the solid principles, why I don't think they're a good idea, and what I talk about to people when they mention solid to me. I'm not claiming to have invented anything here, but this has been my experience over the last few years of being annoyed by solid. Talk originally came about from a discussion with a couple of colleagues. I converted it into a haiku on Twitter, and then Sam asked me to try making it into a talk. I'm going to try really hard not to be the old guy shouting at clouds, but I've noticed in an interview context and in general dev conversation at whatever meetups, someone will confidently volunteer they know all about solid and they can maybe remember the S, what that stands for, but not anything else. And I don't think it's really sort of a personal failing. I think solid is oversold. It's confused in itself. I mean, each part of it is sort of confused. Part of it is advice, part of it is strategy. Some of them are actual goals. The academic evidence that it claims is not borne out when you look at it, with a little closer scrutiny. And it's not really appropriate anymore, I don't think, if it ever was. Open, closed, and the Liskov principle are particularly shaky, I think. There's a lot of tautology in there for two basic concepts in computer science, and it's really what I'd like to call, the two C's: cohesion and coupling. So there's another C in here as well towards the end of the presentation, which is connaissance. So really, this presentation is brought to you by the letter C. Solid, I think, is like exercise, eating healthily, and writing unit tests. We all know we should do it, but no one ever does. Okay. Now, I also want to confess at this point that this is not a preachy kind of talk. I hope it won't be a preachy kind of talk. I once had the honour of maintaining a system early on in my career where one function was 7,000 lines of C code. So I'm definitely not, pointing fingers. Writing software is hard. Maybe not for simple console applications and tools, but for stuff we want to actually be around for a while, right? Libraries, apps, products we want to be able to continue to work with. We want to make sure that the code we're writing means that we can continue working easily into the future without them becoming a big old mess. And it's sort of hard to keep things simple, uncluttered and flexible, so that as you add code, the design doesn't get harder to use and add to in the future. We know we need to organize the code so that we can find things, and we know that we will eventually need to make the changes in the future, either in the short term or in the long term. Every choice you make in writing code means that future you and your team's work can be harder or easier depending on what you choose. Okay, writing code is hard, reading code can be harder. We do more reading than writing, though, and the writing really has to take into account the reader when we're actually doing it. Making a good job of that sort of requires experience, discipline, and since programming is more of an art than a craft, um, more of an art and a craft rather than science, we sort of need heuristics to guide us. Medicine and civil engineering are older professions and have much more grounding in the real world. If you don't build a bridge correctly, you find out pretty quickly. You also find out fairly quickly if your medical procedure didn't work. If you add a line of code in the wrong place, you may not find out for a long time and have people following your choice to build up a set of code that becomes unmaintainable. Fred Brooks, in his book The Mythical Man Month, talked about writing software as managing two forms of complication. Essential, which is the difficulty of the problem domain itself, when the code we are writing, we're trying to capture a model of something in the real world which is just inherently difficult to do. There's also accidental complication, where we get in our own way and we write bad code, if you like. Our tools don't support us very well. Our knowledge of the domain may not be all it could be. Solid and other guidelines that we have are aimed at helping us reduce accidental complexity in the code we write. So let's start with looking at what is solid. Way back in the mid-90s, Robert Martin, and you may have heard of him from sort of the Agile Manifesto, TDD, Clean Code, software craftsmanship movement, all those kind of things. Robert Martin was discussing the 10 commandments of OOP, object-oriented programming, online. And he actually proposed 11 of them, right? The typical programmer's off by one error. And Michael Feathers looked at 5 of those and said, okay, this makes up a really nice acronym. Okay, you take the first letter of each one and it's SOLID, solid. Cool. Robert Martin sort of began a career of sort of writing articles and books based on this clean concept of using solid to try and help with the way that we wrote software. Okay, and he wrote quite a fair few number of articles about these 5 principles. Okay, in a general sense, all 5 of them together, but also he went into depth about each one as well. Okay, so in a way, he happened to be the right person at the right time, and was actually one of the first internet influencers, if you like, way back when. At the time, we're talking about writing OOP code, object-oriented code, in Java. That was pretty much the only game in town for commercial software. So Solid fitted that really nicely, and fitted in with the view of writing software at that time. So object-oriented programming from the early 2000s onwards, say. So it's maybe not so appropriate to the world we live in now, where seemingly everybody is doing JavaScript and OOP is less of a hot thing. So enough with the history. Solid, as said, is 5 principles. Okay, single responsibility, open closed, Liskov substitution, interface segregation, and dependency inversion. So, what's wrong with them? I can't hear you ask. Well, let's look at them one by one. So the first one, the S that everybody remembers, right, is each item of code should have a single responsibility. Okay. Now, right out of the gate, this is often described as a chunk of software should have one reason to change. Now, that's not the same thing as a single responsibility. It's difficult because what we really want I think, is not a single responsibility, but a sense of coherence in the code, that all the pieces belong there. They aren't too big, they aren't too small. Everything belongs there, and there's nothing that doesn't belong there. So we're not mixing things together, right? Which I think is the intent of that. But this principle was originally described in the work of people like Tom DeMarco, and they called it cohesion. And they defined cohesion as the functional relatedness of the elements of a module. Okay, and then this quote kind of came from them. Each software module has one and only one reason to change. And so that's not a single responsibility. On top of that, it's a coding strategy really for me. It's not a principle. So I'm going to cross out single responsibility and I'm going to replace that with cohesion. Next up is the O, open closed. Open for extension, but closed for modification. And this is really about writing code so that you don't depend on concrete types, but instead depend on abstractions. You make software easy to extend to new behavior without having to make lots of changes to existing code. It's really about dealing with that other C, coupling. So coupling is a measure of how quickly your code will break if something about the code you depend on changes. Tightly coupled code may change constantly for small changes in other parts of the system. Open closed gets its name from this person, Bertrand Meyer, in his book Object-Oriented Software Construction from the late 80s. And he had 5 principles of his own. They don't make a good acronym, but you'll notice the 4th one is open closed. And really what Meyer was talking about is not the same thing as open closed in solid. Okay, he's talking about a long forgotten time when software used to be shipped, actually literally shipped, put into a box and sent somewhere, and was difficult to then recall and change. Okay, it wasn't living on a server somewhere where it could be patched and updated at will. And he's talking sort of about strategies that you might want to use to mitigate the fact that you can't kind of get that code back. He's not talking about polymorphism. He's talking more about using inheritance to copy an existing implementation and add to it rather than processing different kinds of subclass to offer different behaviors. Open closed is also in tension with things like Yagni, you aren't going to need it principle from XP. Allowing extension where it possibly won't ever be used. From my experience, applying this sort of principle often results in more horrendous, horrible code. It encourages hierarchies of code to provide openness where it's not needed and often may never be needed. For me, this again is a goal, not a principle. And because it's about coupling, I'm going to cross out open closed and I'm going to write in coupling there. Next in line is L. L is for Liskov substitution. Subtypes can be substituted for supertypes. It's another inheritance-based principle which is really talking about the same thing as open-closed, deriving one type from another and changing behavior, in the common understanding of it. Unfortunately, Robert Martin took some liberties here, and he took Liskov's original research and paraphrased it to better fit the OO world, but in doing that he sort of relaxed it too much. The original constraints that made it meaningful, it changed what the point of the principle was. Now, before I go any further, I've kind of got a couple of things to say about Liskov as well. Many people, when they imagine who this person was, think about them as an old Russian guy who came up with this rule in the 1800s or something, and they're kind of really surprised to find out that Liskov is a woman, and it's Dr. Barbara Liskov, who's an American computer science researcher and she was awarded 2 prizes in computer science that really amount to the a Nobel Prize in any other field, really. So much of what Liskov talked about in the early research looks really, really close to modern programming today. Okay, the original said something like, objects in a program should be replaceable with instances of their subtypes without altering the correctness of the program. This is quite a strict constraint, much stricter than the LSP in Solid. And it's really talking about being able to substitute one object for another and not being able to tell that it has happened from the outside. Right? This is operating in a time when we didn't have abstract data types, so it's setting up rules for that world, not really inheritance and polymorphism. Right? That's a picture of what programming looked like before Liskov, right? Just data and bits and stuff all over creation, okay? This sort of original research came from a time when we didn't have things like abstract data types. Liskov wrote a paper in 1974 based on her research, which basically invented Java. Static type systems, inheritance, data hiding, exception handling, classes, everything but interfaces, I think. A research programming language, Clue, actually invented what we now know as generic type constraints in .NET. She actually talks about not knowing anything about the adoption of her work in Solid until she went looking for sort of what was happening in modern programming. And she found a load of people online debating about what she meant and whether one case or another of OO code adhered or broke her principle. She was actually really quite amused by that. Again, Liskov is in the Solid way of talking about it, is about coupling. So I'm going to cross that one off as well. Next, the I is interface segregation. So this is about having many client-specific interfaces being better than one wide general purpose interface. Wide interfaces may change for many reasons, causing undesired changes in all the code that depends on it. We don't accidentally want to include lots of stuff in an interface because someone somewhere will eventually depend on it, and then the code becomes harder to change. We want to keep interfaces small and tightly focused on what you're doing. This, I'm afraid, is cohesion again. And coupling maybe, because we're talking about interfaces. So interface segregation gets replaced with cohesion. Finally, the D is dependency inversion. We don't want to depend on concrete types, we want to depend on abstractions. We've heard this before, haven't we? This is coupling. We don't want to create types in the body of our code because that means that we're very tightly coupled to those things that we're now depending on. Okay, that's that coupling idea. Okay, we want to move things that we need to perhaps our constructor if we're dealing with classes and have them passed in by whatever is invoking the code. This is classic coupling. And really this is a coding strategy, not a principle. So I think all 5 concepts can be boiled down to 2 concepts really. The 2 I mentioned right at the beginning. Okay, coupling and cohesion. Coupling and cohesion can be often a little bit woolly. Okay, when we're talking about them in computer science. So I want to talk about another CO word, and that's connaissance. I think connaissance is a great tool for thinking about coupling. Coupling is everywhere, and you can improve code not by removing it, but by making it stronger in some places to achieve cohesion and weaker in others to achieve decoupling. 2 software components are connascent if a change in one would require the other to be modified in order to maintain the overall correctness of the system. Okay, that's the definition. Now, I stole this graphic from XP Surgery, and Kevin Rutherford at the XP Surgery. And really what it shows is sort of scale of connascence. So the bottom half is to do with the static nature of code. And the top half, as we go from orange into red, as the dynamic nature of code when code is actually running. So we start off right at the bottom with connascence of name. And really what this means is that for you to call another piece of code, you have to at least know the name of it. Okay, and that's the weakest form of coupling we can get. It's the weakest form. It's the weakest form of connascence, if you like. Okay, if you don't know the name of a function, of a variable, you haven't got much hope of actually referencing it. Next up, connascence of type, so agreeing on the type of something, the type that's returned from a function, the type that you need to create to be able to use something. And as we go up the levels in that static piece, what we're seeing is the amount of coupling, the degree of coupling is actually increasing. Okay, and then when we get into the dynamic, we're talking about running code. Static code is fairly easy to detect and refactor, whereas running code, the connascence in there tends to be much more problematic, much more difficult to actually identify. Okay, but we're talking things about there like number 6, execution order. So the kind of thing where you have to make a cup of tea before you can drink it. The order of something actually does matter. For computer science, something like locking. Timing is to do with networks, that sort of thing. That's where that kind of becomes important. Hardware sort of considerations. Things like, as you go further up, identity, the fact that two pieces of code need to reference the same object and the exact same instance of an object, which is why that's a very, very sort of tightly coupled thing. Okay. Often when we do refactoring and we're trying to improve the structure of code, what we're actually doing is trying to take us from higher up in this stack of connascence and move us further down towards the bottom, where it's actually a little bit more desirable to do that. Okay, and it's important to note that more than one form of connascence can occur in the same piece of code. Okay, it's an imperfect measure, but it kind of blew my mind when I first heard about this, because this gave me much more of a concrete way to look at code rather than thinking about, oh, is it coherent? Is it coupled? Is it decoupled? This gives you an actual measure of some of the things you can point to in code and say, this thing is actually using this type of connascence, and this is kind of where it sits in that whole spectrum of the diagram you can see there. The other thing to keep in mind about connascence is the degree of connascence, so the size of the impact, whether your piece of code is connascent with one thing or 1,000 things will have a huge impact on what it is that you do to refactor and to improve your code. Lastly, I want to talk about a set of guidelines from Kent Beck. I don't think he invented them, but he did write about them. And these are called the 4 elements of simple design, which I think make more sense and are much more memorable than solid. Okay, according to Ken Beck, simple software is appropriate for the intended audience. Okay, the people who have to work with it have to be able to understand it. It should be factored, so there's no duplication of logic or structure. Duplication of structure is preferable to duplication of knowledge, and that's kind of like the dry, don't repeat yourself concept. It should be communicative. Every idea that needs to be communicated is represented in the system somewhere, and it should be minimal. The system should have the fewest elements possible. Again, this isn't a good acronym, but I think it can be simplified into a better form that many of you may have seen before. Okay, so it passes all the tests. Okay, first thing is it should have tests. Okay, making your code testable is a good way of making looser coupling and improving cohesion and actually just making your code better, I often find. We want to, as much as possible, reduce duplication. We want to improve clarity, and we want to make the code the smallest it can be, but enough to maintain the other rules. Okay, and these aren't sort of 4 steps to go through to improve your designs. It's actually a cyclic kind of thing. Okay, because when you're doing things like making things clearer, often means improving naming, which helps with abstraction, and that shows higher levels of duplication. You can factor out duplication, and that means new structure emerges. You have to give a new name to the new thing, and that means you can discover more about the code. You can find new tests which will emerge, or you can find tests and code that need to be removed to become, so the code can become smaller, and you go kind of round and round again. Once you have code that works and keeps working, tests should keep themselves passing if you run them frequently enough. So we can kind of almost forget about that piece. Smallest should also take care of itself because you're improving clarity and removing duplication where possible, and those tend to have an impact on how big and verbose the code is. The thing about clarity and duplication is that the majority of that comes down to finding the right names for things, identifying when names don't match the thing they're describing, or you have names which are at odds with each other. So business logic concepts butting up against database concepts or machine specific concepts. These are all hints that the code is not in the right structure or the names are not correct. I mean, this is the thing that I'm majorly known for at work, is when I'm doing code reviews, is pulling names apart and trying to find the correct name for the thing under consideration, because I think it is so important. A few months ago, I was pairing with a colleague and we had no clue how to solve a problem other than sort of a vague idea and some starting code. And we started out with this code, modified it, and sort of by looking at the names and challenging names and iteratively finding better names and more fitting names as we went, we sort of were able to understand better what the software was trying to do. We understood better what the software looked like and improved the code so that the eventual solution looked like it had been, carefully designed by a genius when it hadn't been. So there we go. We kind of started off with these 5 principles, and I kind of heartlessly pulled them apart into 2 concepts: cohesion and coupling. And then we added in the extra complication of connaissance as a way to think about cohesion and coupling together. We then had the 4 rules of simple design, which I'm kind of making into two rules, which are a cyclic thing: removing duplication and improving clarity in the code. I think it really comes down to this one thing: we should be noticing and improving the names of things. So 5 things down to 1 thing: names. That's all I've got to say. That's my social media tag if you want to reach out to me and talk to me after this presentation. And I think we're just in time to go to questions. Thanks very much.